Assalamualaikum and hi students. So this is a lecture video for BEKG 2443 Engineering Mathematics 2. Okay, still in chapter 3 Vector Calculus. So in this video we will see what is divergence and curl and the Green's theorem. We have Green's theorem in subtopic 3.3. So the definition is given by definition 3.5. Let R be a simple connected plane region whose boundary is a simple, closed, piecewise smooth curve C oriented counterclockwise. Okay, the orientation is counterclockwise. If two functions f and g have continuous first partial derivative on some open set containing R, then if you have this line integral C fxy dx plus gxy dy, so you can solve this by using double integration R dA, and then you have to differentiate your g respect to x, this g respect to x, minus with f respect to y. Okay, so you need to do, and then you need to find what is dA. For the first example, evaluate by using Green's theorem. Okay, you have integration C y dx plus x dy, where C is the circle x square plus y square equal to 4. So you have a circle y and x with radius 2. Okay, counterclockwise. For Green's theorem, it moves counterclockwise. So for integration, you have double integration. Okay, and then y dx. Y is our f. F is equal to y, and g is equal to x. This is fxy, and this is gxy. So for f, we need to find what is df over dy. Sorry, df over dy. So this is equal to 1. Okay, and for g, we need to find what is dg over dx, and this is also equal to 1. For Green's theorem, we have double integral R, and then we have dg over dx minus with df over dy, and then we have dA, the area. So in our case here, we have double integration, and our dg over dx is equal to 1. Minus with, okay, sorry, this should be minus, or else we will get 0. So sorry, this is minus. Okay, so our our g is negative x here. We change it negative x, so this is minus 1. So dg over dx is minus 1, and df over dy is 1. Then we have dA. So for this one, this is R. So we have negative 2 dA. So we have this circle. Okay, so substitute dA with R, dr d theta. We solve this using the polar coordinates. So for polar coordinates, our R limit is from 0 to 2, and the theta limit is from 0 to 2 pi. And then we can solve as usual, the double integral. Okay, solving for double integral in polar, I have the last answer is equal to negative 8 pi. Okay, using Green's theorem, I get this is equal to negative 8 pi. This is minus. In this example, we will see what is the difference between solving this integral C x square y plus 1 dx plus x square dy of using direct integration, line integral, and second using Green's theorem. We will see what is the difference between these two methods. Okay, so first for A. Okay, so over the triangle formed by lines, we have y equal to 0, x equal to 1, and y equal to 2x. So this is line y equal to 2x. This is y and x. Then we have x equal to 1 and y equal to 0. So this is the line. I mean it moved from 0, 0 to 0 to 1 0, and then from 1 0 to 1 2, and then to 1 2 to 0 0. So we have from 0 0 move to 1 0, and then from 1 0 we have 3 segments, 1 0 to 1 2, and last from 1 2 it moved to 0 0. So if we want to solve for A, we need to consider C1, C2 and C3. Okay, for C1 from 0 0 to 1 0, so your x1t is equal to t, okay, and your y1t is equal to 0. You don't have y1, okay, and then C2, as you have 1 0 moving to 1 2, so your x2t is equal to 1, and y2t is equal to 2t, okay, because you have 2t, this is 0. And last for C3, segment 3, you have this 1 2 2 0 0, so your x3t is equal to 1 minus t, 1 minus t plus 0t, right? So 1 minus t, and then for y3t it is equal to 2 multiplied by 1 minus t plus 0. Okay, so you need to solve these 3 line segment first. Solving for the line integral, so this is line integral for C1. Okay, for C1, find what is dx dt, find what is dx dt, find what is dy dt, and then substitute into this C1. Okay, for C1. Okay, so you have C1 here, and this one is line integral for C2. Okay, when you substitute x dx dx into dt, and then dy with dt. Okay, and this is the C3, line integral for C3. Okay, this is x, this is x square, so this is x square y plus 1. Okay, this is dx. Okay, so find what is dx from here and dy from here, then you need to substitute. Okay, as you solve for double integral, you find using directly line integral, you get 5/6. The answer is 5/6. Okay, solve one by one. And then for B, using Green's theorem. So for Green's theorem, from here you have f is equal to x square y plus 1. Okay, this is our f and this is our g. Okay, so our g is equal to x square. Okay, so for f, we find what is df over dx. Sorry, dy. df over dy, we have x square. And for g, we find what is dg over dx. So dg over dx is equal to 2x. Then substitute into double integral. Okay, so we have double integral. We need dg over dx, which is 2x, minus with df over dy. Okay, using Green's theorem. Then this is our dA. dA is the area. So to find the area for this region, okay, so x limit, double integral 2x minus x square. If we want to solve using dy dx, so our x limit is from 0 to 1, and y limit is from 0 to 2x. Okay, so we substitute our y and x limit. X limit is from 0 to 1, and y limit is from 0 to 2x, the area. Okay, so this is equal to 0 to 1. Integrate 2x, we have, integrate 2x minus x square respect to y, we have y, 2x minus x square. Then substitute the limit for y. Okay, so 0 to 1, 2x multiplied by 2x minus x squared dx. And as we solve for double integration, we get 5 over 6 using Green's theorem. So basically, you can solve this question either using directly line integral or using Green's theorem. The last answer will be the same. Okay, will be the same. Another example for Green's theorem. By using Green's theorem, evaluate line integral x squared y dx plus x dy over the triangular path shown in the previous example. So we will use this curve, this smooth curve. Okay, so it's simple. You need to know what is your f, what is your g. So f is equal to x squared y. Okay, f is the one with dx, f dx, g dy. So f is equal to x squared y. So find what is df over dy. df over dy is x squared. And then for g is x. Find what is dg over dx. And this is equal to 1. Okay, considering the same path, so we have the same limit as this one. So to solve for this one, we have 0 to 1, 0 to 2x dy dx. Then we just need to substitute dg over dx, which is 1, minus with df over dy, which is x squared. Okay, now we can solve the double integral. And the answer I get here is 1 over 2. As simple as that. Okay, you just need to know what is f, what is g, and then find df dy, dg, dx. Substitute into the formula for Green's theorem and solve for double integral. The last example for Green's theorem we have here to consider the vector field f equal to negative y x. Okay, so this is for I and this is for j. On the unit disk R, x, y is x squared plus y squared less or equal to 4. So you have a circle with radius 2. And C is boundary of R oriented counterclockwise. Counterclockwise, so it moves to the left. Okay. Evaluate line integral f dot dr using Green's theorem. So you need to find what is integral C f dr using Green's theorem. So in Green's theorem you have double integral. You need to find what is dg over dy, dg over dx minus df over dy to integrate respect to a. So first, our f, the f is equal to negative y. So my df over dy is equal to minus 1. And g is equal to x. So dg over dx is equal to 1. Okay. So we have double integral dg over dx is equal to 1 minus df over dy is minus 1. Okay, and then solve for the find the limit for this. Okay, these two. Okay, we can use r dr d theta. R dr d theta. So the limit for r is 0 to 2 and limit for theta is 0 to 2 pi. Okay. So for this one, we have 0 to 2 pi, 0 to 2, 1 minus 1 is 2r dr d theta. Then continue as usual for double integral. And the last answer is 8 pi. Okay, we evaluate this using Green's theorem and we get the answer is equal to 8 pi. For 3.4, curl and divergence, okay, we start with curl first. If fxyz is equal to fijj plus hk, Then we define the curl of f, written as curl f. Okay, we write as curl f, or we have nabla cross f. Okay, cross f by this. Okay, curl f. So you multiply, you cross, you need to use cross product nabla with f. So you have this. In short, you have to solve for dh over dy minus dg over dz I plus df over dx minus dh over dz j plus with dg over dx minus df over dyk. For curl, we have vector. Okay, we have the vector unit I, j and k because we use the cross product. And for divergence, if fx, yz is equal to fi plus gj plus hk, then we define the divergence of f written as div f, divergent f, or nabla dot f by, okay, for divergent we use the dot products. So we have del f over del x plus del g over del y plus del h over del z. Okay, we have few examples here for curl and divergence. Okay, for a, b, c and d, we need to find what is the curl and divergence of each of the function. Okay, start with a. You have fx, yz equal to x, z, I plus x, y, z, j minus y square k. So you know that your f for a is equal to x, z. Okay, your g is equal to x, y, z, and your k is equal to minus y square. Okay, to solve for curl f, okay, what you need to do is to find what is df over dy. Okay, then find what is df over dz, dg over dx, dg over dz, dh over dx, and dh over dy. Okay, so df over dy is equal to 0. You differentiate x, z respect to y, so it is 0. df over dz is equal to x, dg over dx is equal to yz, and dg over dz is equal to xy. And for fgh, sorry, this is h. And for h, you have gh over gx is equal to 0, and gh over dh over dy is equal to minus 2y. Okay, to find for the curl, so curl is nabla cross f. So this is equal to, okay, easy. So you have dh over dy minus with dg over dz for I. So you have negative 2y minus xy I. Okay, plus with df over dz minus dx over dh over dx. So you have x minus 0 for j, and plus with dg over dx minus with df over dy. So you have yz minus 0 for k. That's it for curl. Okay, I plus xj plus yz k. Okay, and for divergence, nabla dot product with f. This is very simple. You have a scalar. So for f, differentiate f respect to x, you have z. Only z. You don't have ijk. Okay, z plus with dg over dy. So x z plus dh over dz. So you don't have any z here. So it is equal to 0. So the last answer for divergence is equal to z1 plus x. Simple. Okay. And then continue with b. For b, second example for b, you have f is equal to 1, g is equal to x plus yz, and h is equal to xy minus square root z. Okay. Again, find what is df over dy, df over dz, dg over dx, dg over dz, and dh over dx, dh over dy. Okay, for this you have 0, 0, and then you have 1, you have y. For h, dh over dx, you have y, dh over dz, you have dh over dy, you have x. So for curl is equal to x minus y I. Okay, plus with minus 0 minus y j, plus with 1 minus 0 k. So the last answer is x minus y I plus minus y j plus with k. Okay, minus this one, x minus y, 0 minus y. Okay, and you have 1 minus 0. Do not forget your ijk for curl. But for divergence, you don't have any k. Okay, for f, 0, plus with, for g, differentiate respect to y, so you have z, plus this one, for h, differentiate respect to z, so you have minus 1 over 2 z to the power of negative half. So you have z minus 1 over 2 square root z. Okay, for curl you have ijk. For divergence you don't have ijk, you have scalar. Okay, you can proceed with C and D. Try to do C and D, and the last answer for C and D is, okay, for C the curl is equal to 0, and the divergent f, or the dot product of f, is equal to 1, divergent. And for D, curl cross product is equal to 1 over yi minus 1 over xj plus 1 over xk. And for divergence, D is equal to 1 over x plus 1 over y plus 1 over z. Okay, try to do this two questions and check your answer with mine. Okay, so that's all for this video. In the next video, we will discuss 3.5, which is on parametric surface and area, and 3.6 we have surface integral. Okay, so that's all for this video. Thank you.